Hello all, let's start 6.6. 6.6 is inverse trigonometric functions. Trigonometric functions, they are not a one-to-one function. For example, if you see the graph of sine x, if you remember from really bad drawing, let me correct my drawing a little bit at least. If you see like the graph of sine x, the graph of sine x is this shape, right? And you know it's not a one-to-one function. And if it's not a one-to-one function, then they don't have inverse. But if I restrict the domain of sine x, then it becomes a one-to-one function. Now, before doing that, let me write a few sentences here for you. Then I'll start to show how they become a one-to-one function. We can say trigonometric function, or not one-to-one functions. Correct? By restricting the domain of these functions, they become one-to-one. They become one-to-one. What does it mean? Let's see. For example, if I have y equal sine x, or f of x equals sine x, it's not a one-to-one function. If I graph it nicely for you, it's really difficult to write with this pen. I'm trying my best to write with this pen. Here is 0. Here, you know it's pi. Here will be pi over 2. Let's say here negative pi over 2. Let's see the negative side, and here negative pi. Here positive 1, and let's say here negative 1. The graph of sine starts from 0, goes to pi over 2. At pi over 2, sine of pi over 2 is 1. It comes back to pi, and it goes down, and the rest, which I didn't draw it, right? On this side, it goes to negative pi over 2 and goes back to pi. If you look at this graph, it's not a one-to-one function, because if you do a horizontal line test here, your horizontal line intersects the graph more than once, 2 times. It means it's not a one-to-one function. But in those sentences that I put above, I told you that if I put a restriction in the domain means in the values of x. If I restrict the domain of this function, then it becomes one-to-one. How? For example, let's see this graph. Again, I have y equals sine x. Let's say x should be greater equal negative pi over 2 and less than equal pi over 2. I restricted the domain, correct? And if I graph it for you, xy, here, for example, 1, here, negative 1. Zero, pi over 2, negative pi over 2. Now, if I graph the sine function with this restriction only from negative pi over 2 to pi, because I have equal, less than equal pi over 2, I will use a closed circle here. And greater than negative pi over 2, I will use another closed circle here. If I restrict the domain of graph of sine, it becomes a one-to-one. Because if you do a line test here, a vertical line test, you only intersect the graph once. It means trigonometric functions, if you restrict their domain, then they become inverse functions. They become one-to-one function. And you learned at the beginning of our class, at the beginning of the semester, in 6.1, that any one-to-one function, it has an inverse, correct? For example, the inverse of sine x function, we denoted that, first of all, the inverse of sine x function exists because it's a one-to-one, correct? And we denoted by sine, we put here -1. I told you this is the worst notation that I saw in mathematics. Why -1? It's not sine to the power of -1. We read it inverse sine or sine inverse of x. If it's x of x. Or sometimes you see this notation, arc sine. Arc sine x, they are the same. Arc sine means inverse sine. If you check your calculator, in some calculators, it's written arc sine, and some of them you see this symbol, inverse sine. They have the same meaning, correct? Now, our topic here, the topic of discussion in this class is the calculus of this inverse trigonometric function. Let's start with number 1, which is derivatives of inverse trigonometric functions. Let's start with sine. Or let's start the first proof with cosine. d over dx of inverse cosine x is, why not with sine? Let's go in order. ddx of, let's start with sine. ddx of inverse sine x equals 1 over square root of 1 minus x squared when you have this restriction, x is less than equal pi over 2 and greater equal negative pi over 2. Let's prove, I'll do a proof for you why the derivative of inverse sine x is 1 over square root of 1 minus x squared. Let me show you the proof. For you, you have to memorize this. Correct? Later, I'll give you a table of all 6, but I'll prove at least 3 of them for you. Correct? Based on the definition of inverse functions that we start or we learn in 6.1, if I have f of y equal x, then immediately I can write f inverse of x's equal what? Equal what? The domain becomes range, the range becomes the domain. That's the notation, mathematical notation. Now, if I have, for example, sine y equal x, then definitely I can say sine inverse of x should become what? Y. Right? Of course, you have your restriction x between pi over 2 and greater than negative pi over 2. To do the graph, I will start with sine y equal x, and I will show you the proof how and I will find the derivative of sine inverse x for you, correct? Look, sine y equal x. Let's differentiate this function implicitly again in respect to x. Then you can say d over dx of sine y equals d over dx of x. d dx of sine y gives you cosine y dy dx or y prime, which notation you use, equals d dx of x is 1. The derivative of x is 1. Let's solve it for y prime. To solve for y prime, you will divide or you will multiply both sides by 1 over cosine y. Here, these two cancels out. Y prime equals 1 over cosine y. Now, remember from your trigonometry class or from pre-calculus that you studied trigonometric identities. The first one was if you have sine squared y plus cosine squared y, it's always is 1, right? Let's solve this equation for cosine squared. Then from here, I can say cosine squared y equals 1 minus sine squared y. Let's solve it for cosine y. It means take the square root from both sides, correct? The square root of cosine squared y equals square root of 1 minus sine squared y. Here, these two cancels out. Cosine y equals square root of 1 minus sine squared y. Let's take this value of cosine y, which we found here, and we plug in our proof and see what's happening. Then I can write y prime equals 1 over square root of 1 minus sine squared y. Now, we named at the beginning, when we start the proof, you saw that I start with sine y equal x. If sine y is equal x, then definitely sine squared y will be x squared. Let's replace the value of sine squared y in this proof. Then you can write y prime equals 1 over square root of 1 minus x squared. Wow. What was your y prime? Your y prime was d over dx of inverse sine x, right? The dx of inverse sine x then equals 1 over square root of 1 minus x squared. You prove, and this is formula number 1 for inverse trigonometric functions that you have to remember. Correct? I will not do examples right now. I'll show you 3 proofs. Then I'll give you the table of all 6. Then we do some examples, correct? Number 2. D over dx of cosine and inverse cosine x equals negative 1 over a square root of 1 minus x squared. Let's prove it. Proof is the same way that I proved sine, the same way you can prove cosine. Look, if cosine y is equal x, then cosine, inverse cosine x becomes y. Correct? Let's start with cosine y equal x and differentiate this equation implicitly in respect to x. Cosine y equal x, then d over dx of cosine y equals d over dx or d dx of x. d dx of cosine y gives you negative sine y prime equals 1. d dx of x is 1. Solve it for y prime equals negative 1 over sine y. Again, sine squared y plus cosine squared y equals 1. If you solve this equation for sine, then you can write sine squared y equals 1 minus cosine squared y. Then you can say sine y equals a square root of 1 minus cosine squared y. If we plug that value in our proof, y prime equals negative 1 over square root of 1 minus cosine squared y. If cosine, we start with this, cosine y was equal x, then cosine squared y equals x squared. Let's replace this value, plug it in our proof, then you can write y prime is actually d dx of cosine inverse x. Then d dx of cosine inverse x equals negative 1 over square root of 1 minus, instead of cosine squared, you can write x squared. You proved formula number 2. Correct? Number 3. d dx of tan inverse x equals 1 over 1 plus x squared. This is the one that you have to memorize, number 3. I'll show you the proof. Again, if I have tan y equal x, then inverse tan x equals y. Again, differentiate this equation, tan y equal x, implicitly in respect to x. d over dx of tan y equals d dx of x. d dx of tan y gives you secant square y prime equals 1. Solve it for y prime. Y prime equals 1 over secant square y. Remember from pre-calculus that secant square y equals 1 plus tan square y. Let's replace this value here. Then you can say y prime equals 1 over 1 plus tan squared y. If tan y is equal x, then definitely tan square y equals x squared. And if you plug in this value here in your proof, you can say d dx of y prime is actually inverse tan, right? The dx of inverse tan x equals 1 over 1 plus x squared, which I give you as a formula at the beginning. You can do it for cotangent, you can do it for secant, you can do it for cosecant. I will not show all the proofs for you. At least I did 3 of them for you. That from where these derivatives comes in and why we are using, why we are saying that the derivative of our ddx of inverse tan x is 1 over 1 plus x squared. That's the proof, that's the reason why, correct? Again, you are not required for the proofs, correct? Just remember the formulas. That's why I'm giving you this table. Table of derivatives of inverse trigonometric functions. At least 3 of them right now, you know, I did the proof, but again, I will write as a table all of them for you. D over dx of inverse sine x equals 1 over square root of 1 minus x squared. Number 2, d dx of cosine inverse x or inverse cosine x equals negative 1 over square root of 1 minus x squared. Number 3, d dx of inverse tan x equals 1 over 1 plus x squared. These 3 has a lot of use, The other 3, we use it, but you will not see it a lot. This 3 has a lot of use, the first 3. Number 4, d dx of cosecant inverse x equals negative 1 over x square root of x squared minus 1. Number 5, d dx of secant inverse secant x equals 1 over x square root of x squared minus 1. Number 6, d dx of inverse cotangent x equals negative 1 over 1 plus x squared. this inverse trigonometric function, the right side will be the derivatives of inverse trigonometric functions. Now, I will put here a star for you. Star number 1. It means formula number 1 can be written this way also. Again, as I told you, for example, they never gives you a problem like sine inverse of x. They can give you sine inverse of x plus 2. Again, your x becomes a function, g of x or u. Then how to deal with that? I will put just two of them for you. D dx of inverse sine u equals actually to 1 over a square root of 1 minus u squared times du dx. Your u is g of x. And du dx will be g prime x. Correct? Maybe for tangent, I will put also for tangent, star number 2. D dx of inverse tan u, if it's u, it becomes 1 over 1 plus u squared du dx. Again, your u is g of x and du dx will be g prime of x. Right? This table is all 6 inverse trigonometric functions with their derivatives. Correct? Now, let's do some examples. Example number 1. F of x equals inverse sine x squared minus 1, find f prime x. You have your formula. D dx of inverse sine. You see here, I'm not looking for x. My x is actually g of x. That's a function. Then I'll use this one. D dx of inverse sine u equals 1 over the square root of 1 minus u squared times du dx. Now, your u is x squared plus 1, right? You named x squared minus 1, sorry, not plus 1. Your u is x squared minus 1. Then du dx is 2x. Correct? Let's plug in. Then d dx of actual problem, which was sine inverse of x squared minus 1 equals 1 over the square root of 1 minus u. What is your u? Your u is x squared minus 1, and because you have u squared, here is squared, times du dx, which is 2x. Let's simplify. D dx of sine inverse x squared minus 1 equals 2x over the square root of 1 minus. What is x squared minus 1 all squared? It gives you x to the power of 4 minus 2x squared plus 1. Please don't ask me why, because if you FOIL x squared minus 1, x squared minus 1 square means x squared minus 1 times x squared minus 1, right? And if you simplify, you will end up with this. Or use a minus b squared, which is a squared minus 2ab plus b squared, right? I use this one, the same. Now, plus 1 and minus 1 if you, sorry, do not cancel here because I have to distribute the sign also. I have a negative, I'll keep my parentheses here. Then I can say d over dx of inverse sine x squared minus 1 equals 2x over square root of 1, distribute the negative inside, minus x to the power of 4 minus plus 2x squared minus 1. Negative 1 and positive 1 cancels out. ddx of inverse sine x squared minus 1 equals 2x over square root of, if I write this one in a nice order, I will write 2x squared minus x to the power of 4. I will stop here, but again, you can see x squared is common. If you take x squared as common, it will give you x, and you can cancel the x and you can simplify this problem more. But in your book, they stopped it here up to this. If we come up to here, it's still okay. Right? They're really easy if you understand how to substitute, how to deal. Do not forget du dx. Then the rest is algebra, right? When you just apply the rule, it's calculus. The rest of the problem is algebra. Hopefully everyone has a strong base of algebra in this class. Another example. Differentiate. Y equals 1 over inverse sine x. You see, we don't have a formula for this. But can I move inverse sine x up? Y equals sine inverse x all to the power of, because you're moving it up to the power of -1. As soon as you change it to this form, now you know that you have to apply the chain rule, right? It's chain rule. Be careful with the rules, because some of you may not see that it's a chain rule. Oh, no, let's apply the formula. No, it's a chain rule, correct? Then you can say y prime equals negative inverse sine x to the power of -2, you subtract 1, times d dx of the inside inverse sine x, which gives you y prime equals, if I simplify this, I can write as a -1 over, I send it back to the denominator, that gives you sine inverse x squared. Times, what is d dx of inverse sine x? d dx of inverse sine x, you have a formula for, it's 1 over a square root of 1 minus x squared. Correct? Just multiply right as a one fraction and you are done. Y prime equals -1 over inverse sine x squared radical 1 minus x squared. Final answer. Correct? This was all about the derivatives of inverse trigonometric functions. Now, integrals. I shouldn't write all 6 for you because, again, remember the definition. Integrals and derivatives, they are inverse processes, right? Antiderivatives. Then I can say, number 1, integral of 1 over square root of 1 minus x squared. Definitely this one becomes inverse sine x at plus c. Why? Because the dx of inverse sine x was 1 over square root of 1 minus x squared, right? If you go this way now, it gives you integral. I will write at least the 3 of them, not all 6 for you, because the table that I put for derivatives, read it from right to left. The integral of the right is the left side, correct? Number 2, integral of negative 1 over square root of 1 minus x squared. I should put here dx. Here dx equals cosine inverse x plus c. Number 3, integral of 1 over 1 plus x squared dx equals tan inverse x plus c, and the rest 3, other 3 is the same, correct? You can do the rest 3. But this 3 has a lot of use. That's why I put this 3 for you. Now, time for example. Example number 1. Find integral from 0 to 1/4 1 over square root of 1 minus 4 x squared dx. You see here 4x squared, it's not matching my formula, correct? I can change it a little bit. I will do some algebra here. I can rewrite this one, integral from 0 to 1/4 1 over square root of 1 minus 2x all squared. Can I do this? Now I'm in the form 1 minus x squared, and here dx. If I can do that, I have to use the use of u method, correct? Because it's not only x, it's a function, correct? Then my u is equal to x, right? Your u is to x, you have u squared. Then du equals to dx. It means 1/2 of du will be dx. Because I have bounds, lower bound and upper bound, I will change the bounds also, correct? If u is equal to x, when x is equal 0, it means u equals 2 times 0, which gives you 0. If u is equal to x and x is equal 1/4, then u equals 2 times 1/4, which gives you 1/2. Now let's do our substitution, correct? Then I can write this problem actually as an integral, change the bound from 0 to 1/2 1 over square root of 1 minus u squared du, and your du was 1/2 of, you have here dx is 1/2 of du, correct? Replace dx with 1/2 of du because you have u here. Pull out the 1/2 in front. then 1/2 integral from 0 to 1/2 1 over square root of 1 minus u squared here du. Now I know what is this, right? What is this integral? Then this one will be 1/2 integral of 1 over square root of 1 minus u squared gives you inverse sine u. From where to where? From 0 to 1/2. Now plug in the upper limit and lower limit. It gives you 1/2 times inverse sine of 1/2 minus inverse sine of 0, which gives you 1/2. Inverse sine of 1/2. Hopefully you know, you remember when I'm asking what is inverse sine of 1/2, actually it means the sine of which angle is 1/2. You're going opposite, you're looking for angle, or you can push the inverse sine in your calculator and you plug in 1/2, it gives you the angle, correct? Inverse sine of 1/2, which angle the sine is 1/2? Pi over 6, right? Minus which angle the sine is 0? Of course, 0. And if you multiply, it gives you pi over 12 final answer. Correct? This is how you deal with these problems. Last part of your lecture, limit of tan x and inverse tan x. The limit of tan x as x approaching to pi over 2 from the left is, I will not write what is that. Let me explain. Again, hopefully, good teacher in pre-calculus, and you know the graph of tangent, right? If it's 0, this is pi over 2 for tangent, and pi over 2, you have a vertical asymptote. At negative pi over 2, you have another vertical asymptote. The graph of tangent is like this, right? This is the graph of tan x. Okay, now, the limit of tan x as x approaching to pi over 2 from left. When you're approaching to pi over 2 from the left, you are coming towards pi over 2. Where the graph goes? The graph goes to negative infinity. Then the limit of tan x as x approaching from left to pi over 2 is negative infinity. Correct? Number 2. Let me write that one here, show both of them in one graph. Limit of tan x as x approaching to pi over 2 oh, huge mistake here. Approaching from left to pi over 2, not negative pi over 2. I'm sorry, pi over 2. I approach from right. Of course, if I was inside the class, everyone was starting shouting. Let's go back to the first one. The first one, I'm sorry. The limit of tan x as x approaching to pi over 2 from left to pi over 2 here. When you go this way, the graph goes up. It means it gives you positive infinity. Now, the limit of tan x as x approaching to negative pi over 2 from right. when you are going to negative pi over 2 from right side, the graph goes where? To negative infinity. One formula, and this is the second formula, correct? Now, for inverses, what is the inverse graph? Here you have pi over 2. Here you have negative pi over 2. You get two horizontal asymptote, 1 and 2. And the graph of inverse tan is something like this. Now, number 1, limit of tan inverse x as x approaching to negative infinity. When x is approaching to negative infinity, where the graph goes, when you go this way, when you are approaching to negative infinity, your graph goes down, 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 close to vertical asymptote here, which is what? Negative pi over 2. Then the limit of inverse tan x as x approaching to negative infinity gives you negative pi over 2. Number 2, the limit of tan inverse x as x approaching to positive infinity. When you go to positive infinity, definitely your graph goes to where? To pi over 2. This was all about section 6.6. Next day, we will start with 6.8. We will do a jump. I will not cover 6.7 because 6.7 is inverse hyperbolic trigonometric functions. I'm not sure that you covered that one in trigonometry, because if you don't know the simple trigonometry, what is hyperbolic trigonometric functions, then their calculus, then I will explain the inverse of them will become really difficult, and it's a really short-term course, 6 weeks, then we can escape that one, right? I will stop the lecture here and see you next time.